Okay, let's get back into it. So to this point, we've mostly focused on the natural cycles and how the climate changes naturally from an ice age to a warm period back into an ice age. And so now we're going to start talking about more recent climate changes and how we know humans are responsible for it by increasing the greenhouse effect. And so one thing I didn't mention in my background slide is that our Skeptical Science team, we also created, it's called a MOOC, a Massive Open Online Course, which is basically a free online class that anybody can take. And the way we structured it, we have, it's called Denial 101X, so it's a myth debunking class, but it also goes through basic science, so debunking, or going through basic science by debunking myths. And so I've got a few of these videos that it's mostly 5 to 7 minute videos, and they explain these myths and key climate points. And so I'm just going to play this one. It's by Mark Richardson, who is now at NASA Jet Propulsion Laboratory. He's a smart young guy, and he's going to explain the greenhouse effect.
They say it all started with a big bang, and white noise on an old TV set helps to show that. That white noise reaches us in the same way that the heat causing global warming does. This heat comes from the greenhouse effect. Now, what do the Big Bang and the greenhouse effect have in common? We'll talk about the link a little bit later, but let's just start with the greenhouse effect. The greenhouse effect is measured every day by instruments like these. And if we look at our nearest neighbour, we can see just what it's capable of. Venus has big, thick clouds, so that less sunlight reaches its surface than reaches ours. But its atmosphere is about 95% carbon dioxide. This causes a superpowered greenhouse effect. At the surface, it's hot enough to melt lead. Now, how can a simple gas like carbon dioxide be so powerful? The greenhouse effect works like this. We see the sun on a clear day because the gases in our sky are transparent. The sun's rays get to Earth's surface and they warm us up because light is a form of heat. This heat has to go somewhere or we just get hotter and hotter. Earth glows with infrared, a form of light that's invisible to the human eye. Greenhouse gases let through visible light from the sun, but they absorb the infrared from the Earth. They slow down its escape, and they keep Earth warmer. We know how to slow down the escape of heat to keep ourselves warmer. It's called a blanket. Even though the blanket itself doesn't give off heat, we still put one on to keep warm. Now, the infrared heat given off by Earth is invisible to the human eye, but we can see it with this infrared camera. Let's look at an example with a cup of cold water and a cup of hot water. If we look at them, we can't tell which one is hot. But the camera shows that hot water glows more brightly in the infrared than cold water. A similar thing happens in the atmosphere. Greenhouse gases are special, not just because they absorb infrared, but they also glow in the infrared. The glow from the Earth's surface goes upwards. Greenhouse gases absorb some of this heat, and then they glow in every direction, including down towards us. This recycled heat is how the greenhouse effect warms us. We measure it every day here at the University of Reading Atmospheric Observatory, and this is a purgeometer. It has a special window that only allows infrared light through to be measured. Even during a cloudless night, it measures the constant, warming greenhouse glow. Even though the greenhouse effect is an observed fact, there is a myth that claims it doesn't exist. This myth misinterprets a law of physics called the second law of thermodynamics. The second law says that even though heat moves in all directions, overall, heat moves from hot to cold, and not from cold to hot. The myth says that the greenhouse effect doesn't exist because it means heat going from the cooler sky to the warmer surface. But this is a misrepresentation. The greenhouse effect obeys the law. A square meter of Earth's surface sends about 500 watts upwards, so it works like a 500-watt heater. The greenhouse effect sends down about 330 watts of heat, so in total 170 watts goes from the warmer surface to the cooler sky. Heat overall goes from hot to cold, but the greenhouse effect sends some back to warm us up. The myth misrepresents the second law of thermodynamics. Meanwhile, observatories measure the greenhouse effect every day, all over the world. We know it's there. And this is where the Big Bang and static on an old TV come in. Outer space is very cold. It's about 270 degrees Celsius below freezing. But a tiny part of the static on that TV screen is the remains of electronic noise from the Big Bang. This noise contains energy, so it is heat. And despite being unbelievably cold, Some heat has flowed from the frigid outer space to a balmy living room. Now Earth sends a lot more heat into space than the other way round, so thermodynamics is safe. And even though we can't see it, we live under the faint glow of the Big Bang and the much brighter glow of the greenhouse effect. This keeps us much warmer than we'd otherwise be.
Okay, so the key point there was that we have this heat coming up from the Earth's surface and it's going to go out into space, so that's the outgoing heat. And greenhouse gases in the atmosphere absorb that heat and then they send it out in all different directions. So some of it they do send out into space, but some of it they send back down to Earth. And so the more greenhouse gases you add to the atmosphere, the more this effect increases, and so you have more heat coming back down to Earth and less leaving into space. And so the blanket analogy is a really good one because basically the blanket is just it's preventing the heat from leaving your body or the area around your body. Another analogy, we can go back to our bathtub or our water tank. So basically what's happening is that the greenhouse gases are letting less heat escape, and so it's basically like plugging the drain. If you have like a bunch of hair, plugging a drain, then less water is escaping. And so the more greenhouse gases you add to the atmosphere, it's like adding more of your hair into your bathtub drain. So less and less of the water is going out. That makes the heat on Earth, the water level, go up, and so heat's building up and makes global warming happen, which makes climate change happen. So then we're going to have another video. This one's by another colleague, Peter Jacobs, who's at George Mason. He's going to explain how we know, oh sorry, wrong video. This is going to be how we know the carbon dioxide increase is due to human activities and not natural activities, because we know the greenhouse effect is increasing, but there's another myth that how do we know that the increase in carbon dioxide in the atmosphere is due to humans? Maybe it's just natural. And so this video is another colleague from the UK. He's going to explain how we know that carbon dioxide buildup in the atmosphere is due to human activities.
Over the last few centuries, the amount of carbon dioxide, or CO2, in the atmosphere has risen by about 40%. To explain why this is the case, we need to understand how the carbon cycle operates. The carbon cycle describes the flows of carbon between the atmosphere, the oceans, and the biosphere, as shown in this slide. Carbon sources release carbon dioxide into the atmosphere. Carbon sinks absorb carbon dioxide out of the atmosphere. Some of these flows are the result of natural processes. For example, when plants grow, they absorb CO2. However, human activities also play a part. We release CO2 into the atmosphere when we burn fossil fuels. Land use change, such as deforestation, also releases CO2. Ice cores provide invaluable information on how atmospheric CO2 has changed over time. As the Antarctic ice sheet formed, it trapped small bubbles of air which stayed trapped for thousands of years. Cores drilled deep into the ice show us that prior to the Industrial Revolution, atmospheric CO2 had been fairly stable for several thousand years. The carbon cycle was in a state of natural balance. Carbon sources were roughly matched by carbon sinks. Human activity has upset this natural balance. Fossil fuels were formed millions of years ago from the remains of plants. When these plants died and were buried, the carbon was taken permanently out of the active carbon cycle. When we burn fossil fuels, we release this carbon dioxide back into the atmosphere. As a result, CO2 levels have been rising. Scientists became more aware of this after 1958, when accurate measurements of CO2 concentrations were first made at the Mauna Loa Observatory in Hawaii. Together with the ice core record, we see that atmospheric CO2 began to rapidly grow soon after the start of the Industrial Revolution. It would be a bit of a coincidence if this were a natural phenomenon. Furthermore, the increase in atmospheric CO2 has closely tracked the amount of CO2 that we've been releasing. This would be an even greater coincidence if the rise in atmospheric CO2 were natural. In fact, the amount of extra CO2 in the air has consistently been only about half of the CO2 we've released. So the evidence is clear that humans are raising CO2 levels, but not everybody accepts this. One myth is to argue that because the CO2 that humans release is small compared to the CO2 released by nature, our influence must be negligible. Unfortunately, this is incorrect because it only looks at half of the carbon cycle. it fails to consider that carbon sinks also absorb CO2 from the atmosphere. It's the difference between total sinks and total sources that actually governs the rise in atmospheric carbon dioxide. There's a simple analogy that demonstrates that the rise in CO2 is caused by humans. Imagine my wife and I share a bank account which pays no interest and attracts no bank charges. I pay in £1,000 per month, but take no money out. If I notice that the balance rises by only £500, then I know that my wife has taken £500 more out of the account than she has put in. Now, I don't have any direct knowledge of my wife's transactions, but whether she put in £1 million a month or only £1 a month, I still know that she is taking out £500 more than she is putting in. The account obeys the principle of conservation of money. Likewise, the carbon cycle obeys the principle of conservation of mass. The carbon we release doesn't just disappear, it must either be removed by natural sinks or it ends up in the atmosphere. In other words, the change in atmospheric CO2 depends on the difference between the total sources and the total sinks. CO2 levels are rising more slowly than we are releasing CO2. This means that natural environment must be a net carbon sink. It soaks up carbon. It is taking more CO2 out of the atmosphere than it puts in. Nature has been a net carbon sink every year for at least the last 50 years. This fact alone establishes that the increase in atmospheric CO2 is not a natural phenomenon. In fact, nature is actively resisting the rise. I don't need to know the details of my wife's transactions to know that she was opposing the rise in our bank balance. Likewise, we don't need to know the exact strength of the individual sources and sinks to know that nature is opposing the rise in atmospheric CO2. We only need reliable measurements of atmospheric CO2 and of human emissions, which we already have. The error here is in taking an overly simplistic view of the carbon cycle, in this case considering only CO2 sources and ignoring the CO2 sinks altogether. Scientists have developed complex models in order to understand how carbon moves around our carbon cycle. They have done this for a good reason. As Einstein is often paraphrased, everything should be made as simple as possible, but no simpler.
Okay, so this is another example where the overall balance is kind of the key concept. And so as he mentioned, there's the natural carbon cycle balance, where natural sources of carbon put carbon into the atmosphere, and that's about equal to the natural carbon sinks that store carbon, like the ocean and plants. And so the problem is that humans are throwing off that balance by adding extra carbon dioxide in the atmosphere by burning fossil fuels. And so it's kind of similar to the overall temperature. We're throwing off the Earth's natural cycle by increasing the greenhouse effect and adding more heat to the system. So you had a really good example there of how we know the increase in carbon dioxide is due to humans, and it's really because we put twice as much carbon dioxide into the atmosphere as stays in the atmosphere. And so the rest of it, most of it goes into the oceans, and the oceans are storing about half of the carbon dioxide that we're putting into the atmosphere every year. So that's great for us, because if it weren't for the oceans storing that carbon dioxide, then the amount of carbon dioxide in the atmosphere would be increasing even faster, which would make global warming happen even faster. So there are a couple problems with that. One of them being that as the oceans store more of that carbon from human burning fossil fuels, that is, when there's more carbon in the ocean, that increases the acidity of the ocean and makes it more acidic. And when the oceans are more acidic, that's bad in particular for corals. And corals are like a key for a lot of marine ecosystems. And so corals are starting to bleach and die off, and so that's causing all kinds of problems for the oceans and the life in the oceans. And so that's one problem. It's kind of a secondary problem. We call it global warming's evil twin, that in addition to causing the planet to warm, we're also causing the oceans to become more acidic, and that's causing all kinds of problems in the oceans. And then another issue is that at some point the oceans are going to start to saturate with carbon. They're not going to be able to keep absorbing all the carbon we put into the atmosphere as fast. And so as they start to saturate and start to absorb less of our carbon dioxide, that means more of the carbon dioxide we pump into the atmosphere is going to stay in the atmosphere. And so at that point, it hasn't happened yet, we don't think, but at some point it's going to happen, and that's going to cause global warming to go even faster if the oceans aren't slowing down the amount of carbon dioxide we're putting into the atmosphere. So now we've got the next video from Peter Jacobs of George Mason, where he's going to talk about past climate changes and how we know that the current climate change is different and caused by humans.
In February of 2010, researchers in Germany announced the formal name for a recently created element. They called it copernicium. It's what's known as a synthetic element. That means for its entire 4.5 billion year history, before these scientists created it in a lab, copernicium did not exist on Earth. Copernicium is a very radioactive element and is unstable. It has a half-life measured in seconds. But it's a powerful demonstration that humans are capable of changing the world around them. Some of these changes, like the creation of copernicium, are fleeting. Others, like the way we're changing the Earth's atmosphere and climate, can shape the world far into the future. The Earth is heating up, and human activities, mainly the burning of fossil fuels, are the cause. But how do we know we're responsible? Anytime scientists want to answer a question like this, they look at many different lines of evidence. When all of the lines of evidence point to the same conclusion, scientists can be confident about it. And this is exactly what's happening with climate change. First and foremost, we know humans are changing the climate through basic physical principles. Increasing greenhouse gases like CO2 leads to more energy building up in the climate system, and this causes the planet to warm in response. We've understood the physics behind this since the 1800s. But we can be even more confident, because greenhouse warming will leave different fingerprints on the climate than other possible causes. We've known for many decades that increasing levels of CO2 in the atmosphere will produce a unique pattern of temperature change from the surface to the upper atmosphere. The surface and lower atmosphere will warm while the upper atmosphere will cool. By contrast, warming due to some natural factor like more sunlight reaching the Earth would warm the surface and the upper atmosphere as well. The cooling of the upper atmosphere while the surface warms is a fingerprint of increased greenhouse warming, and it's exactly what we can see happening now. We can also look at the ways in which natural forces have changed the climate in the past. We can use this information to rule them out as causing the current change. We know that changes in the Earth's position relative to the sun has caused climate changes in the past, but understanding these changes tells us that they aren't what's happening now. They occur far too slowly to be the present cause, and right now they would be acting to slightly cool the climate overall. We know that the sun's intensity can also change over time, but we have many instruments on the ground and on satellites monitoring solar activity. For the past several decades, the amount of solar energy reaching the Earth has actually decreased, which would also act to cool the climate. Massive, long-lasting volcanic eruptions caused by movement of the continents are capable of heating up the planet by increasing greenhouse gases. But we're monitoring volcanic activity, and volcanoes release a tiny fraction of greenhouse gases relative to human causes. And the greenhouse gases they do emit have a different chemical composition than gases produced by the burning of fossil fuels. The chemical signature of gases building up in the atmosphere tells us that they're from fossil fuels and not volcanoes. One by one, we can look at how natural changes could be affected in the climate and then rule them out. We can clearly see the human fingerprint of greenhouse warming in the pattern of temperature changes in the atmosphere. All of this agrees well with our expectations from basic physical principles. Humans are responsible for climate change. One myth ignores these lines of evidence and claims that because the climate changed in the past naturally, it must be changing naturally now. This is probably the most common myth about global warming, and it's dead wrong. This is like a defense lawyer who claims his client must be innocent of murder because humans have been dying from natural causes for 200,000 years. Meanwhile, the police caught his client at the scene of the murder with his fingerprints all over the murder weapon. Arguing that humans have been dying from natural causes for thousands of years isn't going to convince a jury to let a murderer off the hook. And arguing that climate changed naturally in the past doesn't negate the fact that humans are changing the climate now. The idea that because something happened in one way in the past, it will always happen that way is faulty reasoning. Focusing on the way that things happened before and ignoring all of the possible ways they could happen oversimplifies the issue. This oversimplification leads to jumping to the wrong conclusion, that the climate is changing due to natural causes, when in fact we know humans are responsible. Human activities are responsible for the changing climate. We understand how climate has changed in the past, and this allows us to rule out natural causes. And our fingerprints are all over the warming climate.
Okay, so that's a good explanation of how we know that even though climate changed naturally in the past, the current climate change is different. And so one key is that climate scientists basically make predictions. They say if global warming is being caused by the increased greenhouse effect, we expect to see these various different patterns. Now let's look to see if these patterns are happening, and yes, they are happening. So a good example is that because when you're increasing the greenhouse effect, less heat is escaping into space, into the upper atmosphere and into space. And so you would expect to see while the lower atmosphere is warming, the upper atmosphere is cooling because less of that heat is getting up into the upper atmosphere. Whereas, for example, if global warming were due to more energy coming from the sun, you would expect to see all layers of the atmosphere warming because the heat is reaching all layers of the atmosphere. And so that's a key fingerprint. And they say, okay, if it's due to the sun, the entire atmosphere is warming. If it's due to humans, then the upper atmosphere is actually cooling. Let's see what is actually happening. And they measure the temperature of the atmosphere, and they say, aha, the entire atmosphere is not warming. The upper atmosphere is actually cooling. That is a key signature of an increased greenhouse effect causing the warming. So there's a whole bunch of these different patterns. They're all consistent with what scientists expect to see from human-caused global warming due to the increased greenhouse effect. So we got one last video here. It's from people at this UK website called Carbon Brief, where they put together all the different factors influencing global temperatures over the past century or so, just to show how we know what's causing the recent global warming.
What's causing global warming? It's not the sun, which hasn't changed much since 1850. It's not volcanoes, which cool the Earth for a year or two when they erupt. It's not aerosols. These tiny particles and gases in pollution reduce warming as they cause clouds to reflect more of the sun's energy back to space. It's not changes in land use. The conversion of dark forest to paler pasture, which reflects more of the sun's light, has had a modest cooling effect. Is it ozone pollution? Increases in the lower atmosphere from human activity warm things a bit. Yes, it's greenhouse gases. Rising concentrations of greenhouse gases as a result of human activity are by far the biggest cause. When we compare human factors and natural factors, it's clear who's responsible for global warming.
Okay, so that was a nice explanation, I think, and a nice visual of all the temperature influences of all these different factors, the sun and volcanoes and different human pollutants. One key is that you saw the aerosols, the human pollution that I was talking about when we burn fossil fuels, the sulfur dioxide, those having an increasing cooling effect over time that actually offsets a significant amount of the warming from the increased greenhouse gases. And so as we clean up those sulfur dioxide, that's going to mask less of the human-caused warming from the carbon dioxide. Another key point is that the warming over the past century, and especially over the past 50 years, has been really fast. That's one other distinction from natural-caused warming. When you think back to the charts I was showing of the warming since the last ice age, the warming that we've caused over the past century has been about 20 times faster than the warming that happened as the Earth came out of that last ice age period. And so not only do we have all these fingerprints, all these pieces of evidence, we also see that the warming is happening much faster than it happens naturally on Earth through these natural cycles. So that's the end. I've got, if anybody's interested in looking at our Denial 101X online course, the link is on there at the bottom. You can just type that into your browser and it'll pull up the site and you can check out the course.